Okay, so beginning where we left off with combustion. Looking here, combustion's very easy one to predict products for because the combustion products are going to be the same, the ones that we have you predict. So a combustion reaction is a chemical change in which an element or compound reacts with oxygen, often producing energy in the form of heat and light. So it's exothermic. It's going to give off lots of heat. And for organic combustion, our products are always going to be carbon dioxide and water. So very simple, okay? Example here. This is octane. Octane is what's in cars, the fuel for cars. And as you can see, it's a hydrocarbon plus oxygen giving you carbon dioxide and water. So, you can try the examples here. Very simple to balance. So you go ahead and do those real quick, and we'll take a look at the answers here in just a minute. Looking up here, like the first one, you can still put CO2 plus H2O, and you would balance carbon first, starting with the 3, and then balance hydrogen next, starting with the 4. Add up your oxygens, we get 6 plus 4, so that's 10, divided by 2, so that's 5, and then I'd put my 5 here in front of the O2. Number 2 is very much like that as well, where you divide by 2 and you get a whole number. So they're easy to balance. So this one was 6, 4, 4. Okay. The next two, though, is the examples, of course, where when you divide by 2, you get the odd number and the 0.5, and you have to multiply by 2. But the products are still going to be carbon dioxide and water here. So, like for instance, on number 4, CO2 plus H2O. Here I would balance the carbons first, put a 6 and then a 7 here to balance out the hydrogens. Add up my oxygens. This is going to be 12 plus 7 gives me 19. Divide that by 2, that's 9.5. Put the 9.5 here. Then multiply everybody by 2 to fix it. And that goes to 19. This one goes to 12, and this one would go to 14. So you have a couple of those examples here as well. 3 is similar. It just is less numbers because of the less two carbons and 2 hydrogens. So if you want to check out those answers. But those both 3 and 4 are examples where you have to double at the end because you don't get perfect balancing any other way. Okay. Now looking here at single replacements. Single replacement. There is a little bit of stuff going on with single replacement. You're looking for an element plus a compound gives you an element plus a compound. So one's replacing the other, one's displacing the other. It doesn't matter which way you phrase it. Examples here, showing you an example of the potassium reacting with water. And when you have the reacting with water examples for single replacement, do change them to HOH, like so, because then you now have the H plus cation here that will switch with the other substance. If you don't change it to HOH, it looks kind of funny. But yes, the potassium would switch with the hydrogen there, and that's why we get hydroxide. Just a side note too, the alkali metals and the alkaline earth metals are called alkali and alkaline because when they are put in water, they do form bases. Hence the word alkali is involved there is because it's producing a base. Another example is just showing you a metal that is replacing another metal here. These are both cation versions of single replacement, although there are anion versions where the halogens will switch places and things like that. Okay, but there is a little hitch to single replacements. They don't always occur. Okay, you have to look at the activity series, and you have a table on in your packet that is the activity series, and basically it talks about the cations. Here are the cations, we're looking at the cations. These are versus like the halogens down here. The halogens follow their normal reactivity pattern, fluorine being the most reactive, iodine being the least reactive. But in order to react, you have to be, the free element has to be higher on the activity series, has to be more reactive than the element that's in the compound. So it has enough power to displace it and kick it out of the compound and form the bond. So you have to look at the activity series, and no, you are not expected to memorize it. You will be provided the chart, the table. You just have to read it to figure out if it's going to occur. So let's look at some examples here. If I'm looking at my activity series, once again, if it's water, I change it to HOH here. Look at your activity series. Is potassium higher up than hydrogen on the activity series? Is it more reactive than hydrogen? Yes, so that means the reaction will occur and the potassium will displace the hydrogen. So it'll form KOH. Remember that potassium is going to be a +1. The hydroxide would be a -1. So it's a 1-to-1 ratio to form potassium hydroxide. The free element that forms is hydrogen, and don't forget to make it diatomic because it is diatomic as a free element. Then you would just balance it. Once again, we have 2 hydrogens, so I put a 2 here. That's going to make my hydroxide move to 2. And then this, of course, would be a 2 here. And looking at number 2 here, bromine. Does bromine displace the chlorine? Is bromine more reactive than chlorine? Because we need 2 hydrogens here, we need 2 hydrogens, and we need 2 hydroxides. We need hydrogen here to have 2, so I put the 2 here first, then I have to change my hydroxides, then I have to change my potassiums. So that's how that balances, yes. Yes, the halogens, though, are written up there, they tell you, and if you just look at the table there, the most reactive is what? Fluorine, the least reactive is iodine. So can bromine displace chlorine? No, bromine is not more reactive than chlorine. So no, this one is a no reaction, and you would put no reaction here. Looking at this last example here, we're just going to do a couple, and then you can try some on your own and check out the answers next time. Have you finished this packet? Magnesium. Is magnesium more reactive than hydrogen? Because the magnesium is going to displace the hydrogen that's in the cation position here. Is magnesium higher up? Yes. Yes, so this one does occur. So it would end up being magnesium sulfate, and it would fix in this position because sulfate is -2. Magnesium, when it forms a compound, it goes to +2. And then, of course, you have your free elemental hydrogen floating away. And of course it's diatomic, so you would leave it diatomic, and that one just nicely balances on its own for you. So you can try the rest. We'll look at the other examples next time. So once again, figure out, does the reaction occur? Then make sure that you do the correct ratio based off of their charges. We will come back to the rest. Like I said, we'll look at that next class. So let's look at double replacement. Double replacement, chemical change involving exchange of ions between 2 compounds. So everything in here is a compound. Okay, everything in here is a compound. Generally take place in aqueous solutions, so they're dissolved in water, and they can produce a precipitate, the solid crystals that fall to the bottom, a gas, or a molecular compound such as water. We're going to be focusing mostly on this kind where a precipitate is formed, where you get a solid, the crystals fall to the bottom, or neutralization, where you, of course, form water, which would be the molecular compound. Now, in aqueous solution, a couple of things here to note. Most ionic compounds will dissociate in water. They break apart into their ions, okay? And we're going to write them this way. In next class, we'll go over writing complete and net ionic equations. But today I want you to focus on being able to read the solubility rules and predict whether or not a precipitate will form. Complete ionic equations, you write them all as their ions. So if it says AQ next to it, in the compound you would break it apart into its ions. That's what you would do. And then you would keep the solid together because it, of course, has formed a bond and formed a crystal that falls to the bottom. It is no longer part of the solution. It has now fallen out of solution. Like I said, we'll be focusing on complete and net ionic equations next class. Nitrate and sodium, though, that are not part of the bond that forms the crystal or the precipitate, they are noted as spectator ions. Spectator ions do not participate in the reaction. They sit around and float in the water and watch the show, basically. Watch what else is going on. The silver and the chloride are combining and forming an ionic compound. But the nitrates and the sodiums are doing nothing. They're just sitting in between the water. And in AP, we also pretty much are stuck with always making sure we look at the net ionic reaction, who's actually reacting, who's forming a new bond. We don't really care about stuff that isn't part of the reaction. So you would end up taking out the sodium and the nitrates and getting the net ionic equation, like so. We would cross out the sodiums, cross out the nitrates, because they cancel on both sides, and we would only pay attention to who's doing the bonding. That would be the species silver here ion and the chloride ion forming the silver chloride solid. Those are the only things reacting in this situation. So what we're going to do here is pay attention to our solubility rules to predict whether a precipitate is going to form. Up here in the top part of the chart, these ones are soluble, meaning they do not form precipitates. Okay? Anything with nitrate, always soluble. Anything with acetate. So remember, acetate can be written like this as well, but that's another way that acetate can be written. All acetates, all nitrates, doesn't matter what the other substance is in the compound, they're always soluble. Now, chlorides are mostly soluble with a few exceptions, silver, mercury, and lead. The bromides and the iodides are also falling under that. They're mostly soluble except for with silver, mercury, and lead. And sulfates are mostly soluble. You have strontium, barium, mercury, and lead also being insoluble, exceptions to that rule. So here you're looking at everything that's soluble at the top. If it has those things, it's soluble with some important exceptions. Down below, the bottom part of the table is telling you which ones are insoluble. Insoluble means they're going to perform the precipitate. They're going to precipitate out. So sulfides are typically insoluble except when they're with ammonium or alkali metals or some of the alkaline earth metals. Okay? The carbonates, phosphates, and hydroxides are falling under that same similar rule. They are typically insoluble, will form precipitates, except for with ammonium, the alkali metals. And hydroxides, you have also the same as sulfides, calcium, strontium, barium, will make them soluble. So when you're looking at your examples, let's take a look. Reading your chart here, is sodium nitrate soluble in water? Well, I look up here, is nitrate soluble? Yes, and the alkali metals are soluble, so that would be yes. Is barium bromide soluble? Yes, bromides are typically soluble. Is barium one of the exceptions? No, so this one would be soluble. How about our next one? Lead to bromide. Looking at the bromides again, mostly soluble, but lead is an exception. So this one is not soluble. This one would be a precipitate. And last but not least, magnesium sulfide soluble in water. Well, let's look at our sulfides. These ones are typically insoluble. Exceptions are ammonium, alkali metals, calcium, strontium, barium. Is magnesium one of the exceptions? No, so this one is also not soluble. So when we're looking at examples here now, basically this is how I do it. I go for the sodium's going to combine with the chlorine. The aluminum will combine with the hydroxide. Okay, so I write out my compounds over here. Sodium's +1, chlorine's -1, so that's going to be NaCl, right? The aluminum is +3, hydroxide's -1, so that's going to be Al parentheses OH3. Now I have to decide whether it's soluble or insoluble. NaCl, looking at your solubility table. Is that one soluble? Yeah, so I would write AQ next to it because it's dissolved in water. How about AlOH3? It's a hydroxide. Look at your hydroxides. Hydroxides are typically insoluble. Is aluminum one of the exceptions to that? No, so this one is actually going to form a solid. You put a little S next to it. It's going to precipitate out. Don't forget to balance too. Balancing is fun. So I guess we need a 3 here and a 3 here, right? So you try the next one. See what you get real quick. Do the outers and the innies. So ammonium goes with nitrate, and the lead goes with the Cl. Follow their charges. Ammonium's +1, chlorine's -1. The lead is +2 in this case. The nitrate's -1. So we get ammonium nitrate as one thing. And then our other one is going to be PB what? Cl2, right? Looking here at this example, ammonium, anything with nitrate is always what? What does our table tell us? Always soluble, so this gets an AQ because it's going to be soluble. How about the chlorides? Look at the chlorides. They're typically soluble, but they have a few exceptions. Is lead one of the exceptions? Yeah, so this one you would put an S next to it, right? So try the next couple on your own. You can check your answers right before you go. You have a few minutes, so go ahead and try them. Oh, we didn't balance. You're right. Let's balance. Go ahead and fix this one and balance. So what do we need to put here? We need a 2 over here. Is that about it? Everybody else happy now? Everybody's got the same amount?
We get to the 2 next time.
Oh, yes. We have to put a 2 right here as well. Thank you. So now we're completely balanced, and you can move on to number 3. Checking these answers, of course, there you go. But here we are indicating AQ and S next to these new products, making sure you're checking your solubility rules. We will come back to this next class and look at the other examples real quick. Finish up single replacement and double replacement. But I'd like you to try the ones on the back of the packet. Those ones are all random put together, so you have to figure out what type it is first, then know how to predict it from there.